Hi everyone, check check. How do I sound? Can everyone hear me? Let me know in the comments, please. Yep. Okay, so my mic is on. That's great, you can hear me. Now I'm going to share my screen with you and start with a little announcement for clarification of future plans and schedules, okay? So Zena, I cannot share screen with you. Can you please modify some settings to let me do this? I don't have this option at all. And probably, as you have noticed, I was forced to ask to be a host. Okay, nice. Now I have the option. So I'm sharing the window, and voila. Let me know if you can see my browser. Open notebook. Great. So I started with a little announcement. Probably, as you have noticed, we rearranged our timetable a little due to some rearrangement in Moscow campus, so we are sorry for that. I hope that current state of the timetable is final and permanent, and nothing will affect it till the end of the module. This is my genuine hope, and we'll do our best to keep it that way. As for our next steps, so first of all, that I have to say that we will keep all the control elements as they are. We just a little shifted for a future. Today, we're not going to have tests at all. Today is going to be one practical seminar based on materials of this lecture, of this particular lecture that we going to hold right now. For the following week, you're going to be assigned with the homework. As I mentioned before, it's going to be a test with some numerical and theoretical questions that you have to solve or answer with the multiple choice options. And we go into discuss the completion of the homework next week. Yeah, next week, because next week we're going to have double seminar, right? And on the next week, we also going to have in-class work on estimation value at risk and expected shortfall, all right? And we're going to apply this schema over the rest of the time of the module. So every week when we have double seminar, to this week you're going to be assigned a homework, and we're going to hold a little test in class, okay? So we have 3 this kind of weeks. So everything goes according to the plan, just with a little shift for the future. As for the missing lecture, recording of which I think you've been talking about in the chat, let's do this way. We're going to reserve this extra lecture till the end of the course, and I'm going to post it, let's say, at the last week with the material of the last week, just in case we're going to find ourselves uh, short on time, and in this case, I'm going to use this extra time to record uh, the lecture and post it on an LMS. But if everything goes fine, we're not going to do anything about this lecture. How's this plan? How does it sound? So now it means that we're going according to the plan, and actually this is the lecture number 2. All right. All right. Elena got me. Thank you, Elena. So now so if you have any questions, please ask me now before I start going deep into the material. Some organizational questions. If you want to ask me with a voice, just try to go on air, and Zina will let you in, so you can turn your mic on and speak out loud. If everything is clear, so we're gonna move further, right? Okay, so no questions. So if they arise in the future, so please put them in the chat, and Zina will answer them, or I will answer them later. All right. So now let's get to the point. So the topic of this particular lecture, is estimation of risk measures called value at risk and expected shortfall. Yet this not the whole spectrum of the risk measures that we may face in literature and practice, but this is the 2 key pillar and milestones of current practice. So value at risk and expected shortfall, they are employed and applied extensively in financial risk management. Those 2 risk measures are part of key regulation on banking supervision and setting minimum capital requirements for banks and other financial institutions, as of insurance companies and exchanges. So actually, dealing with these 2 measures, we cover the most of the practical issues. All right. And today we're going to follow a particular workflow. We're going to assume that we are not model developer for a moment, because that's what we're going to do next time, next week, or not next week, but next lecture. But now we're going to put ourselves in the shoes of model user. So we actually, as you might understand, don't need to fully understand the construction and the mechanics of the model to be able to apply it in a real life, and actually assess the quality of the model and the degree it suits our purposes, and actually how it performs in a real life. So we start this particular class with applying the model. So we going to assume that we are actually given the model. So for example, we are junior risk analyst who's been given developed model by his senior colleagues or modeling department division. And the analysts apply this model in order to get some quantities to put in a report or in a chart, or articulate to his supervisors and managers. Okay. And the idea of this lecture is to see how we can actually quantify those measures based on what model we actually have. So what the model that we are equipped with allows us to do. Is it tractable? Is it analytical? Um, can this model be implemented numerically? Is it has some analytical forms and we can, for example, apply some calculus to it? Or it's just a discrete distribution like an empirical one, and we need to apply purely statistical methods and instruments to quantify those measures? Or we find ourselves in some middle position or a mixed position where we have model pretty sophisticated to generate any sample of any size that can uh, represent the actual distribution as close as we need, but at the same time we have nothing, we have no analytical knowledge about the distribution, so we cannot integrate it, we cannot take some statistics derived as some calculus operations, and that's what we're going to do. All right. So all the workflow is going to be built around a particular example. It's a simple example of investing in a single stock. So we going to consider model a very simple market portfolio. And we go into analyze the returns on this portfolio and see how model can be structured and what we have to do with the model structured a particular way to quantify those measures. So let me first of all describe the uh, introductory cells in this notebook, because we're going to use Notebook Collab and apply Python language and Python libraries in order to deal with the data and all the calculation and visualization. So first of all, as we deal with the market portfolio, it's pretty obvious to get some market data, and we're going to do this with Yahoo Finance library that allow us to download market data from Yahoo Finance API. That's what we're going to do here in this cell. So extract the code here, and we see the process of installation. It's not going to take forever to install the library. So this is done. And this particular block deals with importing basic libraries. I'll describe them once briefly for those who never had a chance to deal with a Python. So we're going to use some libraries for plotting and drawing the charts. First of all, we're going to use very basic plotting instruments, matplotlib, and its submodule pyplot. We're also going to use Seaborn as a library for some extra fancy plotting when we need it. We're gonna use Pandas library to store and process the data. We're going to use NumPy all the time as a source for basic mathematical concepts, quantities, and calculus operations. And finally, the central part of our lecture is SciPy submodule stats that contains all the methods and instruments for dealing with distributions. It allows us to fit to the data and manipulate it when it's constructed. So every statistical operation that we run is going to be assisted with this submodule. All right. So we import all these libraries and packages as well. And so let's construct our simple portfolio that we go into investigate. So here is a very simple operation of downloading historical data on Apple corporation stocks from 2016 to 2020. It's going to be a data frame. So here we can see a tabular information with the date of observation as an index. And as a matter of fact, you see some other information, other columns containing primarily price information. It's just different types of daily prices. So I'm sure that you're aware of those types as an open price, higher, low, close price. Here is a special type adjusted close. This is the price we need for analytical reasons because it's adjusted for dividend payments and splits that allows us to ignore price changes not related to the market view. Okay, because probably you know that prices tend to fall when the dividend is paid, and prices of stocks also change proportionally to the size of the split. All right, but this technical changes has nothing to do with the random nature of returns and price changes according to the market view and market activity. All right, but that's the nature of the risk we actually care about. So we're going to use this adjusted close prices. The volume is not interesting for us, so we're going to leave it aside. And now let's take a look at the price trajectory. From this data frame quotes, I'm going to take the single column, which is going to represent Pandas series. All right. Yeah, it's gonna be in the next cell, but now I'm going to show you the difference between different types of prices. So close and adjusted close. So just to make sure that you, just to let you make sure that those prices are different and they have slightly different dynamics. From this particular graph, we can clearly see that trajectory is something oscillating, containing randomness, and investing in stocks, in formatting market portfolios definitely has something to do with the randomness and risk assessment. But prices itself, it's not what we actually care about. From the first lecture, you probably remember that we actually think of financial results, and prices in themselves and value of my portfolio itself is not actually a result, because so I'm more concerned about changes of those values, and I need some indicator that will represent those changes to me. So now I'm going to pick a particular measure of price changes. Definitely, I could use just price difference, but it's not a quite good choice, because most of the time investors in analytics, they care about relative measures of changes. So they actually care about the returns. So how many cents I'm going to lose on any dollar I invest in particular stock or any other instrument. So we're going to apply two styles of returns, namely log returns. This is the formula above, and arithmetic or simple returns. They just calculated differently, but uh, um, exactly represent the dynamics of the prices. So it's just a matter of preference and choice, which style we're going to use um, in our modeling and assessment. For this particular lecture, we're going to stick to um, arithmetic returns, is simple returns. But if we talk about the future and actually process of modeling that we're going to discuss in the closest future, we will prefer actually log returns because they have nice statistical properties and allows to simplify models and allows for several nice and pretty close approximations that are very widely accepted in the practice. So in the future, we're gonna work with the log returns, but today we're gonna go with arithmetic ones. So this is so here you can see the formulas, analytical formulas, and that's how those calculations are implemented in Python. So as I was saying, I took one column out of data frame quotes, and this is actually um, series of pandas containing labels and index the dates of observations and prices as an observations of those dates. And I apply just basic calculations from the Python to see what the returns are. We also can see here that log returns and arithmetic returns are pretty close to each other when we talk about pretty small values. So for example, if we care about daily returns and observe daily returns, those two concepts are pretty close to each other in quantities. And that's where you can get the intuition why we're going to use log returns in the future as they have nicer properties and they pretty close to the arithmetic returns, which are we more concerned about, for example, for reporting, because actually our management or shareholders are more concerned about physical returns, which are represented by arithmetic simple returns. All right, so now we're going to deal with returns as a representation of particular outcomes of my investment. And now we're going to deal with this as a series. Please pay attention that during the calculation, we're going to obtain none in one of those observations, so we have to drop it from the consideration to not ruin further calculations. So that's the technical realization of this. Drop none is a way we drop missed observation. We have this missed observation because we actually cannot calculate return on the first date we observe price of stock, right? Because we need two prices for the calculation of return. We need current price and previous price. So it's obvious that we have no previous price for the very first observation in our table. Out of luck, but nothing that we can do about, just to drop it out. Okay. Great. Now let's take a look at the series of the P&L, because that's what we go into model. Yeah, definitely we can see randomness here. This is the pretty um, fam familiar picture to your eyes uh, if you still have memories. Yeah, yeah, absolutely, Anya. Lecture is recorded. It is always recorded. It is recorded automatically when it starts, so don't worry about it. Okay, so we definitely see the randomness, and um, it looks not very stationary, but somewhat. So we can see some clusterization of oscillation in Galina. I will answer your question later, all right? Okay, so here's the series of return. Okay, but now we actually concerned about what can happen in the future. So for example, this is the historical realizations um, of the experiments of my risky investment when I was opening position in some point in the past and consider what's going to happen the next very day. So all the series represent potential outcome for the investment portfolio that I can construct at the end of this sample. So for example, just at the very beginning of the um, uh, 2021, right? And I'm concerned about the distribution, as I was saying at the first lecture. So here's the question. How can I represent the distribution of daily returns? And the first option that we can come up with, it's just do nothing but deal with empirical distribution of past returns. So let's take a look at the empirical distribution. So I'm going to construct the histogram of this series. So this actually implies that I think that only cases that I observed in the past over the last 5 years, because the length of this history is 5 years. So only scenarios and uh, returns that I observed in last 5 years can happen on next very day. All right. So this is the model. This is the most assumption-free model. So just everything that happened in the closest past can happen tomorrow. And I represent future distribution, the distribution of future losses that I potentially can face in a 1 year, on a 1 day horizon. I represent it with an empirical distribution of the past daily returns. Okay, and so here's a little code that allows me to construct this histogram. In this particular case, I use Seaborn method displot, and I put as an input my return series, and I use the kind of plot that I would like to see as a histogram. I also specify number of bins that I would like to break my sample into. So that here in this picture, I'm going to see 50 bins of this kind, if they're not empty at least. And I also put true to the parameter of kernel density estimation. just to get a perception of the potential uh, um, density probability function that generates that could generate this particular sample. Okay, so this is just the first uh, perception that I can get from the data. Why is axis goes close and not return? Um, I think it closed. Well, it's called closed because returns just inherited the name of the series from the series prices. All right, see here, I took the column from the data frame, called this array prices, but the internal name of this series was adjusted close. And then when I perform any calculation and just create new instances, new arrays, internally they inherited the name of the series, all right? And as you can see, I never specified the axis name here. It's just uh, inherited it from the array returns, okay? Good. Okay, now let's play a little with uh, some particular class of distribution, some analytical distribution, or some distribution that can be numerically implemented in Python or already implemented in Python as a candidate for this sample of returns. Okay, and to do this, I am going to need a stats module that I imported at the beginning of this notebook, and call it SS for short. Okay, you can see it right over here. So this is the stats submodule of SciPy, and I use alias SS for short. So remember that SS here is a stats. Okay, stands for the stats. Good. So what this module actually allows me to do, this is a super cool module that allows me first feed particular class and or family of distribution to the data. It also allows me to run some calculations of basic statistics on those distributions with the fitted parameters. And it also has uh, some analytical tools that allow me to assess the quality of fitness. So actually, I can definitely fit any model to the data, and the best way this model actually allows me to do this. But at the same time, I'm going to see if the degree the model fits the data is actually meaningful and gives me the reason to think that the model may be applied for the practical purposes. All right. So let's start with very basic and probably naive choice of the distribution, but the distribution that we all know very well, and probably no one is going to stuck with this distribution in practice. So we start with the normal distribution. We use the instance norm that represents submodule having all the methods concerning normal distribution. We use the method fit to actually fit the parameters of this distribution to our returns. And then we go into print the parameters and see what they are. Okay, so yeah, actually we can see that we estimated two parameters. First of them is just the mean, and another one is a standard deviation. You know that unilateral normal distribution is fully defined by these two parameters, so the mean and standard deviation. And actually now we can elaborate on these quantities and see what they tell us. First of all, we understand that uh, daily mean return is very close to zero. At least uh, it has uh, uh, much smaller magnitude than standard deviation. So this is a particular degree um, of the greatness of standard deviation upon mean. So this is what we actually uh, take as a granted, because it says that on a daily basis, we actually cannot think of great profits. It's not what we actually expect. So if we would like to uh, gain some uh, meaningful expected return, we need to hold portfolio for a long time, not just one day, and not even a week, probably for a month. On a daily basis, the um, expected return is much smaller uh, in respect to the risk, which is represented here um, with the standard deviation. And the standard deviation here is as great as 2%. So actually, on a daily basis, you expect a kind of range plus minus um, 6, 6% if we use 3 sigma rules to cover the region of the most probable outcomes. All right, so it's kind of wide range of possibilities from minus 6% to 6% of profit. Okay. All right, so let's see if this fitted normal distribution fits our data pretty well. We can use numerous graphical and statistical um, tests and tools to see uh, if our model fits data well. Here I'm going to limit our consideration why we should fit normal distribution, as we can calculate mean standard in this series. No, well, Dmitry asked why we should fit normal distribution if we can calculate mean and standard deviation in a series. I can't say that you should do this. It's just I just try to unify the workflow and use the same kind of realization of any calculations, just not to confuse you on a further calculations. It's clear that we can calculate mean and standard deviation even on a paper. It's pretty easy to do. But I would like you to use some unified methods, general for any distribution that you can fit with a Python, just in order to be able for a future just to switch from one distribution family to another, and do not think of picking or rewriting any calculations on particular parameter. Everything you should know that everything you have to do is just to specify probability distribution family, and then apply the same comment that will return you all the parameters that you need and that are actually associated with with the distribution. Okay, so there is no difference in calculating mean and standard deviation this way compared to the methods in pandas. Okay. All right, so let's take a look at the Cuckoo plot that allows us to see if the fitted distribution fits the empirical distribution pretty well. And this is the kind of standard picture that we can expect when we try to represent distribution with a heavy tail, with a distribution with a light tail, like normal distribution. In this case, you can see that all the quantiles of your empirical distribution not going to fit theoretical quantiles of the fitted distribution. So, for example, these two discrepancies on the left tail and on the right tail is telling us that normal distribution cannot represent a probability of extremely extreme losses or extreme profits. All right, so that means that actually probability of getting extreme results in empirical distribution is much higher than implied by theoretically fitted distribution. And probably that means that we should choose another distribution with a heavier tail to represent our data more closely. All right. We also can apply some other graphical techniques. I'm not going to spend much time on them. You can Google them and play around with this code at home, just to make sure that you pick right distribution for your data. The rule of the thumb, as usual, is pretty usual. You should pick the distribution that is the simplest in terms of parameters and tractability that fits your data accurately enough. So, for example, if I switch from normal distribution to student t distribution and apply the same techniques, I'm going to see the alignment of all my observations along the line represented by theoretical, line represented ideal consistency between the data and fitted distribution. Okay, so from these pictures we can conclude that a student distribution fits our data pretty well. Okay. All right, so what we're going to do now, we're going to use these three types of distribution for the calculation of value at risk and expected shortfall. We're going to use historical empirical distribution as a discrete one, just as a discrete representation of potential future returns. We're going to use normal distribution as an analytical distribution, and as an alternative that allow us to calculate in a closed form, or at least numerically, value at risk and expected shortfall. We're going to use t-student distribution as well, and we're going to use them as an image of very complicated model that we cannot actually deal with in terms of calculation, so we cannot apply any analytical. How can we understand that distribution fits better not looking at the graph but with some numerical methods? um, Here is the deal, Dmitry. You can use, first of all, some information criterion that combines the likelihood of getting some empirical distribution or sample from a particular uh, distribution family, and at the same time it combines um, the complexity of the distribution itself in terms of degrees of freedom represented by parameters. All right. So, for example, you can use uh, uh, some information criterion. I can provide you examples, let's say outside of this lecture. Um, for example, for your, okay, we're going to include some in homework, okay? Just to deal with this. So we provide the hints and the information, what those criterions are and how to implement them, okay? So let's do some calculations. So we start with numerical distribution, empirical distribution, and let's calculate several value at risk measures based on the confidence level that we would like to ensure during this calculation. So probably, as you remember, value at risk is a quantile measure of the risk. So it associates with the confidence interval. So let's say if I calculate 95% value at risk, it means that I'm concerned about the loss level that is not going to be exceeded with 95% of probability. So actually, it cuts off the extreme zone, which is pretty unlikely to happen. In this case, I leave only 5% of probability to those extreme losses to happen. But at the same time, if I'm not lucky and I get into this region, I'm going to face losses much greater than I was expected to have. So value at risk is kind of measure of extreme losses, but regarding the confidence level that represents the level of, let's say, the degree of typical losses. So like 98%, 95% of. So this is the region that I'm going to face in a series of the investments. Okay, so like in a series of experiments. Okay, so 95% that I'm going to face losses not greater than value at risk. So if I change the confidence level and, for example, to greater one, like 99%, definitely it will shift my my risk measure to the left. In this case to the left, because negative values and negative returns represent losses. So I'm going to think of greater losses, potential losses, if I'm going to deal with losses I'm facing 99% of all the cases. All right. And Let's calculate those values from empirical distribution. So actually from discrete distribution. To do that, we can apply uh, internal method of pandas. It can be applied to pandas series and data frames as well. This method is called quantile, and it has several parameters, but we need to actually care about two of them. One of them is probability of extreme events. So this is a probability of that we live in a tail, right? So this is the probability mass that we try to cut off with this quantile. As we deal with the left tail, it is supposed to be very small, right? So only 1% probability I have to live in this tail. That's why I use cut-off probability level 1%. And another parameter that I have to specify is interpolation. As we deal with discrete distribution, the quantile measure is not uniquely specified, because actually, in contrast to the continuous distribution, when there is the only way we can find, there is a single value that represents quantile, so the value exactly cuts the distribution in two parts. One of them is a 1% and another one is 99%. Dealing with empirical distribution as a discrete one, we actually can set the range of them, of those values, and each of those values will actually correspond to the value left in the tail. In this case, we need to additionally specify the way we deal with this region. So in this case, dealing with the value at risk, we use the higher value of the region that can represent quantile. So that means I'm going to pick the minimal value of the extreme losses that I can face and that can occur during my investment, that ensures that I face losses greater than value at risk, at least at the level that I specify as a confidence. So if I want to be sure on 99% confidence interval, I'm going to take the value on the right-hand side right here. If I'm dealing with the right tail, I'm going to specify an interpolation parameter as lower. The intuition is the following. Actually, I'm going to use value at risk in practice, for example, for setting discounts or setting capital. And I'm not interested in posting some extra money that actually do not contribute to the confidence level I specify. So I like to see the minimum amount that I have to post to ensure confidence level that been specified in a regulation in my risk policy, or that I voluntary, arbitrary chose. Okay, so here I have three calculations, three value at risk on different confidence intervals. Those quantities are represented on this chart with the vertical lines. So the red one stands for value at risk at the 99% confidence level. So we can see that it constitutes 5.26%. So this is kind of a huge loss, daily loss of 5%. If I'm less concerned about my losses, so I would like to ensure only confidence level on a 95%. I actually mostly care about losses of magnitude as big as 2.67%. And if I'm very light about the consequences of my investment, and for example, I can tolerate extreme losses that can occur with a 10% of probability, I actually set the limit on 1.79 of percent. All right. So the more conservative I am, the more confident I would like to be about the coverage of the typical region of potential realized returns, the greater value at risk is. Okay. So for example, if I want to be ensured that I'm going to be ready to cover any losses with a 99% of probability, I set my value at risk and the capital on 5.26% level. All right. This of course, this works in terms of the model that I apply, which is empirical distribution here. Okay. So this is a very simple. Okay. Now let's take a look at calculation of expected shortfall. Well, the expected shortfall represents the expected value of extreme returns. So those returns that are greater than value at risk. Okay. So if dealing with the value at risk, I was concerned about the region that I'm going to find myself by the end of my investment, and I'm going to see the result in this particular region. The expected shortfall actually says, assuming, given the fact that I actually wasn't lucky and got extreme losses, so what those extreme losses are likely going to be. All right. So in this cell right here, I calculated value at risk and expected shortfall. Sorry, I forgot to specify interpolation here. Interpolation higher. Okay. Yeah, right here. It's slightly different. And so I calculated value at risk on 99% of confidence. And I calculated mean return of those historical returns that I experienced in the past, but those who are greater in magnitude than arena, interpolation is not necessary for uh, expected shortfall calculation, but it's more important for value at risk because, well, by the definition, value at risk is the minimum loss level that ensures my confidence interval. All right. So if I would like, so if I want to ensure that value at risk cuts off the tail with a probability mass that is not greater than I specified. So, for example, if I specified confidence interval 95%. So that means that on empirical distribution, the weight of the tail that I cut off with a quantile or value at risk is supposed to be not greater than 5%. And I can do this multiple ways. Actually, there are a region of the values that satisfy this condition. But from the economic point of view, I would like to find the minimum value of those values because I would like to use them for economically meaningful operations like setting capital requirements. And I'm not actually interested in setting extra capital that cannot actually contribute to my confidence. So I know that I need to ensure confidence level 95%. That's the minimum level that ensures this, okay? It's not going to affect expected shortfall because actually expected shortfall is calculated over actually realized returns. So, but the value at risk, the quantile of the empirical distribution, can be set not only with actual observations, but can be set in between them. That's why we use this interpolation method just to ensure that we pick right observation, some particular observation, and it's minimum observation of those that correspond to my confidence confidence level. Okay, so I can actually change. Can we please say again what was the numbers var mean together? So value at risk is loss level that cannot be exceeded with a certain degree of probability. So this degree of probability corresponds to my confidence level. For example, if I calculate value at risk on 99% confidence level, that means that I'm interested in loss level that can be exceeded. So that means that in future I may face the losses that greater than value at risk only with 1% of probability. Why 1? Because I would like to be confident on 99% level. Okay. Expected shortfall is expected level of those losses that are greater than var. So, for example, if we can see on this picture, value at risk on 99% confidence level is 5.26%, and represented by this red vertical line. So this particular value of returns is actually represents var. Okay, so this is extreme loss, some of the extreme loss that probably I will see. Expected shortfall is the expected value of this losses in tail that cut off by var and represent expected value of those extreme losses. So if let me demonstrate it. Let me demonstrate it here. So no, let me do it here. As I was saying, for example, we can calculate 95% value at risk as a quantile on our empirical distribution. I can see, so about war with probability, we may face losses more than in the future. No, not 1%, but 5% here. So you can see the confidence level in this particular example is 95%. So I leave 5% of chance to observe in the future losses greater than 2.68%. Okay. So this is the level. Okay. And expected shortfall, it is an expectation of those losses that are greater than value at risk. So, for example, I'm trying to get a perception how bad things can go to me if I'm not going to be lucky and face returns not not corresponding to the value at risk. Okay, so I'm not going to see results from this region because this is the region that represents to me favorable outcomes, positive values, and negative values, but not critical ones. They are pretty probable and not too extreme in terms of magnitude. But this tail represents very extreme losses. So calculating expected shortfall, I'm trying to identify potential of loss in extreme events, okay? So that means I'm going to probably, on average, face losses like 4.47%, about 4.5%, if actual losses occurring in the future are going to be greater than value at risk. Okay? Okay. Okay. That's what we're gonna do. That's what we going to have if we deal with empirical distribution. So this is a discrete distribution. We just deal with actual observation. Everything that we do is actually try to split this distribution with some levels corresponding to the confidence interval. But what if we actually can apply analytical distribution? So let's take a look what's going to happen if we apply normal distribution. Yeah. Okay. So if I deal with a distribution that is implemented, for example, in Python, that means that my notebook actually can calculate cumulative distribution function and its values. Notebook can calculate density probability function and its values. just knowing the class and parameters that specify um, that correspond to specific version of the distribution. So if I fit the distribution, and now I can specify the distribution as an instance of, uh, of Python, actually I can apply internal methods like calculating uh, quantiles. And that can be done with a formula in fourth line in this cell. It's pretty easy because everything that we need the specified distribution. And everything that we need is just to apply the method ppf that corresponds to quantification quantile. As a parameter, as an argument of this method, we just put in confidence interval. So for example, if we apply level confident, if we try to calculate value at risk on 95%, so here we're going to deal with the 5%, okay? And we can analytically or semi-analytically calculate the quantile and value at risk from particular shape and form of the distribution. Okay, not very hard to do. So in our case, we apply normal distribution and apply this formula, and actually we can see the value of value at risk on 95%. Let's put it on a graph. PPF stands for percentile point function. So this is internal method of stats, and it can be applied to any distribution that is implemented in stats. Okay. All right. So let's compare these two values. So here the red vertical line that represents empirical estimate of value at risk, and yellow vertical line that represents analytical or parametric value at risk that we just calculated in this cell. And we actually can see that these two values are different. So dealing with some kind of distribution, we can also calculate var, but implied by particular form of distribution. And here I would like to mention one thing, that dealing with empirical distribution, you can actually okay. Olga asking about the break, and what time is it now? Yeah, I think we're gonna have a break. So we continue after a short break. So we're gonna have 20 minutes break, right? Okay. All right. So I'm not going to turn off the translation. I'm not going to go close the translation, and then I'm going to be back in 20 minutes, all right? So if you have any questions, please write them here in the chat, and when I'm back, I'm trying to answer them, okay? And we're going to continue this material on next lecture as well, just to finish it out, all right? Good.